All right, here we go. So today's video is about friction. So up until now we've been talking about friction, right? And we've always used the symbol FF to represent friction. And so remember, that force of friction is the force applied by the surface that an object is resting on, or I guess I should say in contact with. And that force is going to do one of two things, all right? So up until this point, we've been talking about friction in very generic terms. So now we need to start learning about the two different types. All right. So the idea is if the object is already sliding, okay, if it's already scooting across the floor or whatever, friction doesn't want the object to move anymore. All right. And so once the object is already sliding, the friction that tries to prevent that motion, that works against the motion, is called kinetic friction. All right. And so we'll use the symbol FFK to represent that force of kinetic friction, okay? So that would be something like this. If I drag this chair across the floor, the entire time that it's moving, there's kinetic friction. If I push it and slide it, the reason that that stopped sliding eventually was, again, because of kinetic friction, okay? Now, there's also what's called static friction, all right? Static friction is the type of friction that exists when there's some force attempting to make an object move, but friction is preventing it from sliding, okay? So if I come over here and push gently on the chair, then static friction is preventing it from moving, okay? You know, it's usually more noticeable on a heavy object like this. If I push this table like this and try to push it, it's not moving because of static friction, okay? So those are the two types of friction we're going to talk about, kinetic friction and then static friction. Obviously we'll use FFS for because it's static, okay? So let's learn some finer details about these two things, all right? We're going to start with static friction, okay? Static friction is actually the one that I think is a little bit harder, okay? So here's what you need to know about static friction. So first of all, it only occurs if the object is not sliding across the surface, but the object would be sliding if there wasn't any friction, okay? So right now I'm pushing on this chair and it's not moving because of friction. If there was no friction, it would be sliding, right? Because there'd be nothing working against its motion. Okay, so, you know, anytime you try to slide a box across a table but don't succeed, that's because of static friction. Okay, weirdly, when a car speeds up, let's make a little drawing here. Okay, so here's my car, right? Okay, so right now the car is at rest, right? Let's suppose the car wants to speed up. Okay, so what's going to happen is the wheels are going to spin, right? The driver presses the gas pedal and the wheels spin around this way, right? Now, if there was no friction, what would happen is the wheels would just spin in place, you know, just, and the car wouldn't go anywhere, right? Okay? But what happens is there's static friction, and so the tires don't actually just slip. What happens is the road grips the tires, prevents the tires from slipping backwards, and pushes the car forwards. Okay? The same thing when you walk, right? The floor pushes you forwards when you push back on it. Okay? So, those are some examples of static friction. Anytime the two surfaces do not slide across each other, you're then talking about static friction. All right. So here's the deal with static friction. I like to describe it as being lazy. All right. It's always going to exert as little force as it can, but enough to prevent the two objects from sliding across each other. All right. And often that makes the net force zero, but not always, as is the case with the car speeding up. Right here, friction is actually providing a force that makes the net force on the car not zero, right? That's why it speeds up, okay? I'm guessing we'll have to talk about this more in class, and that's fine. But I guess the big thing I want to make sure you understand at this point is that often the net force is zero, but not always, okay? All right, so here is a very important thing that you need to know about friction. So anytime two objects rub together, there is a maximum amount of force, oh, my board needs to be calibrated here, a maximum amount of force that static friction can exert, okay? And how much force friction can exert depends on a couple things. All right, so the first thing it depends on is what's called, the first thing it depends on is the two surfaces that you've got rubbing together, all right? The two surfaces result in what's called a coefficient of static friction, okay? And the symbol we're going to use for coefficient of static friction is, it's the Greek letter mu. So it's basically a lowercase letter u with a little tail on the front, all right? And then we're going to use a lowercase letter s to indicate static, all right? And what that coefficient of friction is, it's a ratio, okay? And basically what it represents is sort of how rough the two surfaces are, okay? So two surfaces that are smooth, so that they're kind of slidey, those are going to have a real low coefficient of friction because they're not very rough, okay? So an ice cube on another, on an ice skating rink or something is going to have a very low coefficient of friction, closer to 0. Teflon is a very slippy surface that they put on baking pans and such. That has a very low coefficient of friction, all right? Now, as the surfaces get more sort of grippy or sort of rougher or more coarse, I guess would be a more technical term, you get a larger coefficient, okay? So when we say a large coefficient, we basically just mean close to 1, okay? It's very rare for a coefficient of friction to be larger than 1, although it does happen from time to time, all right? So why do they make car tires out of rubber? Oh, because they're grippy, right? They grip the road, okay? So if you're on a dry road, the coefficient of static friction between the tires and the road is 1. On wet road, it drops all the way down to 0.6, okay? So that coefficient of friction is just sort of a rough measure of how rough the two surfaces are. It's not a measure of force, it's just a ratio, okay? Now, the second thing that the friction depends on is how tightly the two objects are pushed together. For us, that means normal force, all right? So if you think about rubbing your hands together, so take your hands and put them together and rub them together, and they get nice and warm, right? If you push them together tighter and then do it, they get a lot hotter, a lot faster. That's because there's more pressure or more normal force of one hand pushing the other hand, okay? So this right here, this is the reason why people often confuse weight with friction. A lot of times people say, oh, I can't move this thing, it's too heavy. And that's not the issue. The idea is if there was no friction and I pushed this, it would move, okay? But because it weighs a lot, that means there's a large normal force, which means there's a lot of pressure pushing this table down against the floor, results in a large normal force and therefore a lot of friction, okay? So these are the two things that determine our maximum amount of friction, all right? And so the notation we're going to use to represent that maximum friction is this: force of friction static max, okay? So how do we find it? So here is our equation. So the idea is, at any given instant, the actual amount of static friction force acting on your object is going to be less than or equal to this maximum value. Okay, and to calculate that maximum value, you just multiply this coefficient of friction. Remember, that's just a number that measures how rough your two surfaces are. You're going to multiply that by your normal force. Okay? So probably the easiest thing to do at this point is to just kind of jump into an example so you can kind of see how this all works, all right? So let's do this. So in this example, we've got a 20 kilogram box sitting on a floor. Coefficient of static friction between the floor and the box is 0.65. And it wants us to make a free body diagram and describe what the box will do if Roy pushes the box horizontally with each of these forces, okay? So let's make a little drawing. It's always a good place to start. The mass of the block is 20 kilograms. And I know that my coefficient of static friction is 0.65. All right, so when you make a free body diagram, you can always start with your gravity. So 20 times 9.8 is going to give us 196 newtons, negative because it's down. All right, Roy's force is going to be horizontal, so the only other vertical force here is our normal force. So in this example, our normal force is fortunately just the same as our gravity, right? So, remember, these two values, this coefficient of static friction and this normal force, together determine our static friction max. So let's figure out what it is. It's coefficient of static friction times normal force. So our coefficient is 0.65. Our normal force is 196. So multiply this out, and you get a number. So you get a number of 127.4 newtons. All right. So this number is important because it's telling us that in this scenario, as Roy is pushing our block, so Roy is going to push this way. Here's our force from Roy. All right. Friction can exert any force up to and including 127.4 newtons. Okay. So what that means is, in example A, here's my drawing. So for part A, I'm going to just draw the horizontal forces here. So the idea is you're still going to have, your gravity and your normal force are going to be there. In part A, what's happening is Roy pushes with 80 newtons, and friction's like, no way, dude. I don't want that box to move. I have 127 newtons in my pocket. So it's going to push back, but remember, friction is lazy. It's just going to exert enough to prevent the box from moving, right? We know the box isn't going to move. That means our net force has got to be 0. So my force of static friction is actually not going to be 127. It's only 80, right? Because that's enough to make my net force 0. Okay? Now, in part B, clear up my board here a little bit. Okay, now in part B, Roy pushes with 100 newtons. And again, I'm being sloppy. I'm ignoring my normal force and my gravity just to save time here for you. So now my force of Roy is 100 newtons. Oops. 100 newtons. And now friction is like, well, you're getting closer, but I still have 127 newtons I can use, right? 127 newtons. So friction's going to push back with negative 100 newtons for the same reason, because that'll make the net force 0 and it'll prevent the box from moving. All right? So now when we get to box C, oops, when we get to part C, now what happens is this. Force of Roy is 130 newtons. Friction wants to prevent it from moving, right? So, but the problem is friction can only exert 127 newtons, and that's not enough to prevent the motion. So what's going to happen here is our net force is not going to be 0, and it's actually going to start moving. All right? It begins moving in this case because it can't exert enough force to prevent the motion, right? 127 newtons wouldn't do it. Okay? And so to finish this problem, we actually have to learn about kinetic friction, right? Because now the box is actually sliding. And so we need to deal with kinetic friction. So we'll do that in a minute. All right. So we actually can't finish part C yet. Okay. All we can say at this point is that it'll move and it'll accelerate, right? Okay. Now, before we get to static or to kinetic friction, we got to do one other real quick thing, which is this. Sometimes we got to go the other way. All right. So let's do this example. So this time we got a 50 kilogram box sitting on a floor. So let's draw it. 50 kilograms. Let's go ahead and put in our force of gravity. 50 times 9.8 is going to be, what, negative 490 newtons. Roy pushes the box, presumably horizontally. I should have written that. Horizontally. And discovers he needs a force of more than 300 newtons to make it move. So since he's just pushing horizontally, my normal force is going to be 490 newtons. Here's my force of Roy. So what this is telling me is that if Roy exerts 100 newtons, friction will push back with 100 newtons. If Roy pushes with 200 newtons, friction will push back with 200 newtons. If Roy pushes with 299 newtons, friction will push back with 299, right? And it's saying that he needs more than 300 to get it moving. So it sounds like if Roy exerts anything up to and including 300 newtons, then static friction can exert anything up to and including 300 newtons, right? So this is a weird way of me telling you what the maximum force of static friction is, right? I'm telling you how much force he needs to get it to move, and so that's telling me the maximum force of friction, all right? Now this is kind of a gray area. A lot of times it won't say more than, it'll just say he discovers he needs a force of 300 newtons. So, so that means that your maximum friction is 299.9999999, which you just round up, right? Okay, so anyway, so let's finish this. So, we're trying to find the coefficient of friction. So it's just this. Force of static friction max is our coefficient of static friction times our normal force. So, coefficient is static friction max over normal force, which for us, let's see, our static friction max we decided was 300 newtons. Our normal force is 490. Divide it out and you get 0.061. Cool. And remember, no units on that because it's just a coefficient. All right. So this is actually how they calculate these coefficients of friction. Is they take some object and set it on a table and they figure out how much force they need to get it moving. That tells you the maximum force of friction, and then they can experimentally calculate the coefficient. All right? So that is the deal with static friction. All right, so now kinetic friction. So kinetic friction is what exists, the type of friction that you need to deal with once your object starts sliding. All right, so important stuff to know. First of all, kinetic friction only occurs if the object is already sliding across the surface. All right? It always acts in the opposite direction of the slide. All right, so in this first example, if Roy is sliding a box across a table, so here's the force of Roy, the box is sliding this way, that means friction is going to go this way. Not because Roy is pushing to the right, but because it's moving to the right, okay? So I really like this next example better. Remember the Superman stopping the sliding bus, right? So here's the idea. Here's our bus that the giant monster had thrown. The bus is sliding this way. He's trying to get the baby. There he is, baby. That's a weird-looking baby. So even if Superman wasn't there, friction would be trying to stop it, right? Kinetic friction, because it's sliding. Now, Superman coming in here and trying to stop this thing doesn't change what friction is doing, right? Now it's just Superman and friction working together to stop it. All right? So please don't make the mistake of thinking that the friction opposes the force. It doesn't. Kinetic friction opposes the velocity. All right? The idea is this school bus in this example is moving to the right. Friction doesn't want it to, so friction's going to push to the left, no matter what direction Superman pushes it. Okay? All right, and then finally this last example, if a car is spinning its wheels, remember we talked about the car speeding up a minute ago? If the car's wheels are spinning, the same thing kind of happens, right? So here's your car. Whoa, my car got ugly. So as the wheels are spinning around this way, friction doesn't want them to, and so friction's going to push back against it, right? And hopefully there's enough friction to get you out of the ditch or whatever. Okay? So, that is the deal there. Now, it turns out that kinetic friction depends on the same two things that static friction does. The only difference is the coefficient of friction has a different number. And the big thing I want you to notice is this, that your coefficient of kinetic friction is usually less than, occasionally it's equal to, but never bigger than your coefficient of static friction, okay? So once again, this coefficient of kinetic friction is determined by sort of how rough the surfaces are. The rougher the surface is, the bigger the coefficient of friction, and it also depends on the normal force. All right, now the nice thing about kinetic friction is, unlike static friction, your kinetic friction is a fixed value. So once your object is sliding, automatically you can find your kinetic friction by using this equation. You just multiply whatever your coefficient of kinetic friction is by your normal force. Okay? So, for example, in this last problem we had figured out that 130 newtons would get the box moving, right? So this is that example I said we have to come back to. So let's come back to it. So here's what we've figured out so far. So we got our 20 kilogram box. Gravity is pulling it down with negative 196 newtons. Our normal force is positive 196 newtons. And we discovered that Roy's force of 130 newtons, remember we had figured out that our static friction max was 127.4, I think it was. So your train of thought should be, oh, 130 is bigger than 127.4, so it slides. Ah, that means I need to think about kinetic friction. So let's find our force of kinetic friction. So the force of kinetic friction is our coefficient of kinetic friction times our normal force. So that's 0.4, right, because that's our coefficient of kinetic friction, which I gave you now that we know what that is, times our normal force. Normal force is 196 newtons. There we go. So multiply that by 0.4, and it gives you 78.4 newtons. Okay, so notice there is less kinetic friction than there is static friction. That's why if you're driving your car, once you start sliding, you're in trouble, right? Because once you start sliding, there's automatically less friction, so you're in even more trouble. Okay, so here we go. Let's put in our kinetic friction. It's negative because it's pointing to the left, 78.4 newtons. So now I can find my net force and solve this thing. So let's see, my net force in this problem is the force of Roy plus the force of kinetic friction. I'm not going to worry about gravity or normal force because they cancel. So I've got 130 newtons plus negative 78.4 newtons. So that gives you what, 51.6 newtons for net force? And then clearly you could use that to find your acceleration, right? Just by doing net force over mass. Okay? But the point is, once you know the object is sliding, you automatically switch over to kinetic friction and solve the problem that way. Okay? All right, and one last example, I think. Yep. All right, so here we got a 30 kilogram box, mass 30 kilograms. Roy discovers if he pushes the box horizontally with a force of 300 newtons, then the box will accelerate at 4.5 meters a second squared. Find the coefficient of kinetic friction. All right, well, let's see. We should automatically put in our gravity. So 30 times 9.8 gives you what, negative 294? Since he's pushing horizontally, my normal force is going to be big enough to cancel that. So positive 294. All right. Now, giant, super important rule of thumb. If I give you the acceleration, find your net force. All right, so I gave you the acceleration and the mass. So let's see, our mass is 30 kilograms. Acceleration is 4.5 meters a second squared. So that gives you what, 135 newtons? Okay, so cool. Now I know my net force. So to find the coefficient of kinetic friction, I need to know, well, let's see. Here is what we know. We know that the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So the coefficient is the force divided by the normal force, right? So we need to know our kinetic friction force. So I think we can do that, because what I know is this. I know that my net force is the force of Roy plus the force of kinetic friction. So 135 newtons is my net force. Force of Roy is 300. And I can solve for my kinetic friction, right? So subtract 300 from both sides, and I discover that my force of kinetic friction is negative 165 newtons. All right, to make this add up over here. So I think we're just about done. Negative 165 is our kinetic friction. Normal force is 294 newtons. Oh, don't worry about the negatives here, because your coefficient of friction should not have a sign associated with it. And so whatever 165 over 294 is, it looks like it's 0.56, and there's your answer. All right, that is that.